In this video, I'm going to be talking about how we describe motion with diagrams and data tables. You already know that physics is concerned with understanding physical events, and we're starting with things that we can see when we're looking at motion. And so in order to analyze and understand those events, we need to have some way to talk about them. We need some kind of visual representation. And so we've been talking about how we have particular words such as speed or velocity or acceleration or displacement to help us understand a particular event. But also along with words, we can use illustrations or pictures to better understand what's going on. And those pictures can take the form of graphs or diagrams or just numbers themselves or numbers in equations. I want to start by talking about an old machine that was used to describe motion because we're going to be using sort of a facsimile of the results of these sorts of machines in some of our classwork. And that is a ticker tape timer. So this ticker tape machine would put a dot on a piece of paper, on a long, thin piece of paper that's kind of like a piece of tape, at a particular time interval. And so what you would be left with would be a trail of dots that provide a record of that object's motion in a straight line. We're just talking about straight line motion here. And the distance between the dots then represents how that object's position has changed. As a result, dots that are close together, well, there's not much change, and so that means that the object was moving very slowly at that point. When the dots are very far apart on your ticker tape, then there has been a significant change, or your object is moving quickly. Now, we don't use this machine anymore. We've got a variety of computer-based technology to help us do these sorts of motion analysis, but we do use illustrations of that tape when we're talking about motion. So those illustrations are usually called motion diagrams or oil drop diagrams or just ticker tape or dot diagrams. And what they do is give you an idea of the relative speed. Is something going slowly or quickly? They can show changes in velocity and acceleration. They're not going to give you particular numbers. There's not a value associated, but you can kind of look at the big picture and see what's happening by looking at how the dots change. So let's do a little bit of analysis of these 5 dot diagrams or ticker tape diagrams. We want to look at the dots in position across the piece of tape and think about how does this arrangement of dots show us something about the speed of the object's motion, about the velocity or the rate of change in speed or direction. In this case, there's no directional change because everything's moving to the right. But then also acceleration, how the velocity is changing over time. So looking at our first one, at ticker tape A, you can see that the dots are pretty evenly spaced across here. So we can talk about the speed by saying it is a constant speed. It's not increasing, it's not decreasing, it's just holding. If the speed is constant, then velocity, which is just speed with a direction, is also constant. So we have constant velocity in the rightward direction or the positive direction. And then acceleration is how is velocity changing. In this case, since velocity is not changing at all, it's a constant velocity, our acceleration would be 0. Then going on to ticker tape B, you see we have dots close together here in the beginning, and then they spread out further apart until we get this rather large gap between the last 2 dots. And so this tells us that our speed is increasing over the tape. The velocity then would also be increasing, again, in the rightward direction, and the acceleration would be increasing in the rightward direction. So when both your velocity and your acceleration are moving in the same direction, that object is speeding up, which we can kind of already figure out by looking at these dots. Ticker tape 3 is showing us the opposite situation where our first 2 dots are very spread apart, but as we look across the tape, we see we get down to ones that are very close together. So in this case, we do have a decreasing speed. Our velocity is then decreasing. It's decreasing in a rightward motion, but the acceleration is going to be in a leftward motion because overall it is slowing down. And in that case, the direction of the motion and the direction of the acceleration are in opposite. The acceleration decreasing is going to be or acceleration is going to be in a leftward direction, so the motion's right and the acceleration is left because the combination then causes the object to be slowing down. Ticker tape D shows us an object that has a constant speed to begin with. These dots are all about the same distance, not very fast, but it is moving at a constant speed, and then it starts moving faster as these dots get farther apart. So in order to describe this, you would have to be talking about both parts of that motion, that the object starts off at a constant speed and constant velocity with no acceleration. Then the speed and velocity are increasing in a rightward direction, and there is acceleration also to the right. Our last ticker tape has a variety of things happening to it. This little dot here is just a typo. It was on the original illustration. I think maybe looks like a bug got squashed on the tape. But anyway, this particular object is starting off at a fairly high speed, and so far as what the tape is showing us, it's slowing down here and then speeding up again without ever really hitting a constant speed. So our speed changes are first slowing down and then speeding up. Velocity also would be decreasing and then increasing. And our acceleration is going to be first towards the left, causing it to slow down, and then towards the right, causing it to speed up. The next type of diagram I want to talk about are vector diagrams, and vector diagrams give us an indication of both how big something is, the magnitude or the number associated with it, at least in a relative sense, and the direction of that particular force or motion. We're going to be dealing with vectors a lot more in future units, but I wanted to introduce them at this point because for motion that's in a straight line, we can also use some vectors. Arrows are used in describing things with vectors, and the size of the arrow matters. So a big vector is a greater magnitude, a greater number of whatever we're talking about. And then whatever direction that arrow is pointing is showing you the direction of the motion or the force or whatever you're talking about. So in this first example, we have constant velocity because we see the little vector arrows are looking exactly the same out of all the little car diagrams. And then the second illustration is showing us a accelerating car because our vector diagrams are velocity. That little velocity arrow is very short in the beginning and it's very large here at the end. So this is just to introduce this idea that we use arrows, and the size and which way the arrow is pointing matters when it comes to describing motion with vectors. Here's an illustration that you may remember from earlier studies about space. We have the moon orbiting around the Earth, and the moon is kept in its orbit by two particular forces, and so we have some vector arrows here showing you the forces. We have the force of gravity that is pulling the moon towards the Earth, so our vector arrow is pointing towards the Earth, and that is balanced by the force of velocity, or the speed that the moon is traveling at, because that would cause the moon to want to travel in a straight line, so that vector arrow points in the direction it would want to travel and gives us an idea of its strength. Of course, gravity and velocity will balance out, and so then it keeps the moon traveling on this dotted path, roughly equidistant from the Earth all the way around. So this is just an illustration of showing how we are using vectors to try to explain what's going on. And then finally, we want to get down to data tables. We have done quite a bit with data tables and thinking about graphs, and we can use them again sort of the same way, comparing row to row, to answer some questions about these different types of motion and what's going on. So the first type of data table I want to talk about are position time data tables. So they're comparing the position of a particular object, where it is in space, how far it's traveled, to the time it's taken to get there. And so position time data tables are giving you information you can use then to figure out things about speed and velocity, and of course displacement. So I have two data tables here for us to look at. I should have labeled them. So we'll call this one A and this one B. So let's look at the numbers that are here. We see that our time is in seconds, and we're going from 0 to 4, and then we have various values in meters for the position. So first of all, what's the displacement? How much has our object moved over this time period? Well, object number 1 has moved to 16, a value of 16 meters, and so it's going to have a positive 16 meter displacement. And then in table B, we see we go from 24 down to 0, so in this case we've got a negative 24 meter displacement. How about the velocity? How has the velocity would be a speed value with a direction attached, and a speed value, of course, is the distance divided by time. So in this case, our total distance would be 16, and the time would be 4. So our velocity would be 4 meters per second in a positive direction. And then on the other table, we're going from 24 down to 0, so the distance would be 24, the time would be 4 seconds, and so we have a 6 meter per second in a negative direction velocity. Remember, we've got to have some sort of directional indication on velocity because velocity is a vector. The little delta here means change. So how does speed change over time? Well, if you look at each individual rows, we can see each time the position on this one has moved forward by 4 meters from 0 to 4, 4 to 8, 8 to 12. So the speed over here is constant. There's no change really in speed. At our other table, we are going from 24 to 18 to 12 to 6 to 0. So again, our speed is constant. It is changing by 6 meters per second each second that we go along. So it's a constant speed, not speeding up, not slowing down. And then our speed value, of course, is the same as our velocity. And so in this case, it would be 4 meters per second, no directional indication needed, or 6 meters per second for table B. So B is moving a little bit faster, but it's moving in a negative direction, whether that be to the left or to downward. We don't have enough information here to let us know. The second type of data table that you'll be analyzing are velocity time data tables. And you need to make sure you know whether you're thinking about position time or velocity time because they can look very similar. But velocity time data tables help you think about the velocity and the acceleration. So first, let's think about the acceleration that's being shown by these two tables. I'm going to label them A and B again. Just looking at the data, first off, we notice that our velocity is increasing from 0 to 16 meters per second in table A, and it's decreasing from 25 to 5 meters per second in table B. So to figure out the change in acceleration, the average acceleration, we use the formula that is the change in velocity over time, or our final velocity, so V final, minus our initial velocity, VI, over that total time. So this is the formula for average acceleration. And so to apply that here, we've got our final value on table A of 16, and then minus 0 for the initial value, and then that's over 4 seconds. So the acceleration for table A, if we go do the math, it would be 4 meters per second, because the value for velocity is meters per second. Because remember, in acceleration, you have 2 time units. So we can write this as 4 meters per second squared, or just 4 meters per second per second. On our second table, our final value is 5, so we would have 5 minus we're thinking meters per second, 5 meters per second minus 25 meters per second, so that's going to give us a value of negative 20 meters per second. We divide that by our 4 seconds, that's the total, and then we get a final value then of 5 meters per second, or since I have more room over here, I can write 5 meters per second squared as the average acceleration for table B. Now this is a negative 20, so it should be a negative 5. So our acceleration, it is slowing down, but this greater number, 5, negative representing the direction. So 5 meters per second squared is compared to 4 meters per second squared for table A. Tells you right away that even though B is slowing down, it is slowing down faster than A is speeding up. With the data tables, it's fairly easy to to figure out the average velocity, because basically we just look at the middle row. As long as your time values are all increasing just 1 unit at a time, we just look to see what's in the middle. So it'd be 8 meters per second for table A, and it would be 15 meters per second for table B. How about our speed? How is it changing? Again, delta means change. We've already talked about how our velocity going from 0 to 16 says that it is speeding up for table A, and going from a velocity of 25 meters per second down to 5 tells us that table B, the object, is slowing down. And then the direction of acceleration, because acceleration, remember, doesn't just mean stepping on the gas like in your car, but acceleration in physics means a change in velocity. So the direction of acceleration for table A is going to be rightward. It's going to be in the same way that the motion is moving. It's because it's speeding up. And then on table B, the direction would be leftward. It's moving in the opposite direction of the motion because the object is slowing down. So the direction and the direction of the velocity, and our velocity is positive for table A and negative for table B. So we can also write positive and negative over here. The acceleration and velocity are moving in the same direction when an object is speeding up, and in opposite directions when an object is slowing down. All right, so thinking about what we've gone over in this video, are you able to analyze a dot diagram? Think about how those dots, their spacing, what that tells you about the speed or the velocity or acceleration of that object. Can you explain how vector arrows are used to show the two vector qualities of magnitude, or how big it is, and then what direction it is pointing in? And can you take a look at these various data tables and analyze the numbers to talk about speed or velocity or acceleration? Those are the key points of this video. If you're still feeling really confused, go back and have a second listening, and hopefully that'll help you and clear up your questions.